Modern civilization runs on something we rarely think about. Electricity is not just convenience. It is coordination. It is communication. It is refrigeration, navigation, finance, medicine, water pressure, transportation. At night, cities glow like constellations turned upside down. Highways pulse with movement. Data flows invisibly between towers and satellites. Everything feels stable. But above all of it, beyond the atmosphere, something far more powerful is always in motion. The sun is not quiet. It is not static. It is not constant. It moves in cycles. And sometimes, it erupts. In 1859, long before power grids and fiber optics, before microchips and satellites, the Earth experienced a solar storm so intense that telegraph systems, the most advanced communication network of the time, began to fail. Operators reported sparks flying from equipment. Some were shocked. Telegraph paper caught fire. Auroras, normally confined to the polar regions, were seen as far south as Cuba and Hawaii. Night skies glowed red. Miners in the Rocky Mountains woke believing it was dawn. The event would later be named after the astronomer who observed it, Richard Carrington. But in 1859, the world was not electrified. There were no nationwide power grids, no satellites in orbit, no air traffic control systems, no refrigerated supply chains. Today, the same magnitude event would not be an inconvenience. It would be a systemic shock. To understand why, we need to understand what actually happened. The Carrington event was caused by a coronal mass ejection, a massive burst of solar plasma and magnetic field released from the sun's surface. When that energy cloud struck Earth's magnetosphere, it induced powerful geomagnetic currents in the ground below. Those currents traveled through long conductive materials, like telegraph wires. Today, those same currents would travel through high-voltage transmission lines, substation transformers, long-distance pipelines, and undersea cables. The infrastructure that connects modern civilization is, in many ways, more conductive than the telegraph network of the 19th century, and far more interconnected. There is a reason solar storms concern grid operators. The largest transformers in the United States are not mass-produced. They are custom-built. They weigh hundreds of tons. Manufacturing lead times can stretch many months, sometimes more than a year. If enough of them were damaged simultaneously, replacement would not be immediate. It would be logistical. Now here is the deeper question. Was 1859 a once-in-history anomaly, or part of a pattern? The sun follows an approximately 11-year cycle of magnetic activity. Solar maximums bring increased sunspots, more solar flares, and more coronal mass ejections. In 1989, a geomagnetic storm caused a blackout in Quebec, leaving millions without power for hours. In 2012, a massive coronal mass ejection crossed Earth's orbit. It missed our planet by days. Had the timing been slightly different, researchers estimate the impact could have rivaled or exceeded the Carrington event. Near misses rarely make headlines, but they are part of the record. The question is no longer whether the sun can produce such an event. We know it can. The deeper question is how modern civilization would respond if it did, because in 1859 sparks flew from telegraph lines. Today, the stakes are different. Our world does not simply use electricity, it depends on it. If a solar superstorm of historic scale struck Earth in the modern era, what would happen next? And how prepared are we, really, for something we know has already happened before? In late August of 1859, the night sky caught fire. Observers across the globe reported a strange glow on the horizon. Reds, greens, and shimmering curtains of light danced far beyond the polar regions where such displays normally live. The aurora was so bright that miners in the Rocky Mountains woke in the middle of the night and began cooking breakfast, believing the sun had already risen. Newspapers could be read outdoors at midnight. But the beauty masked something violent. Just days earlier, an amateur astronomer named Richard Carrington had been observing the sun through his telescope when he saw an intense flash erupt from its surface. It was a solar flare, the largest ever recorded at that time. 17 hours later, Earth was struck. The impact triggered powerful geomagnetic storms that rippled through the planet's magnetic field. At the time, the most advanced technology on Earth was the telegraph. Operators reported sparks flying from their equipment. Some received electric shocks. Telegraph paper caught fire. In several cases, systems continued transmitting messages even after being disconnected from their power supplies. The current induced directly by the storm was enough to keep them running. For a brief moment in history, human technology was overwhelmed by a star 93 million miles away. That event is now known as the Carrington Event, and it happened before light bulbs, before airplanes, before radio, before the electrical grid. Now imagine that same level of solar violence striking a world covered in transformers, satellites, fiber networks, GPS systems, aviation routes, digital banking, refrigeration chains, hospital infrastructure, and data centers that hold the memory of civilization. The sun is not calm. It breathes in cycles, roughly every 11 years, waxing and waning in magnetic intensity. During solar maximum, the frequency of flares and coronal mass ejections increases. Most pass by Earth harmlessly. Some graze us, but occasionally one is aimed directly at the planet. A coronal mass ejection is not light. It is not heat. It is a massive cloud of magnetized plasma, billions of tons of charged particles hurled into space at millions of miles per hour. If the magnetic orientation aligns just right, it can couple with Earth's magnetic field and inject enormous electrical currents into the ground itself. Those currents travel through long conductors, pipelines, rail lines, undersea cables, and most critically, high-voltage power lines. Transformers are the backbone of modern electrical systems. They are also vulnerable. Large extra high-voltage transformers are custom-built, weigh hundreds of tons, and are not sitting on shelves in warehouses waiting for replacement. If enough were damaged simultaneously, recovery would not be measured in hours, or days, or even weeks. It could take months or longer. In 1989, a much smaller geomagnetic storm caused the Hydro-Quebec power grid in Canada to collapse in just 90 seconds. 6 million people lost power. That was a fraction of the intensity of 1859, and our dependency has only grown. The deeper question is not whether the sun can produce such an event. It already has. The deeper question is how modern civilization would respond if it did. In 1989, a geomagnetic storm struck Quebec and collapsed the entire provincial power grid in less than 90 seconds. 6 million people lost electricity almost instantly. Transformers overheated. Protection systems tripped. Transmission lines went dark. The cause was not sabotage, nor war, nor mechanical failure. It was the sun. A surge of charged particles ejected days earlier struck Earth's magnetic field and induced powerful electric currents in long conductors, especially high-voltage transmission lines. Those currents flowed into transformers never designed to handle them. They saturated. They overheated. Some were permanently damaged. Hydro-Quebec restored power within hours in many areas, but the warning was clear. Modern grids are vulnerable to geomagnetic disturbance. And that storm was not even close to the most powerful on record. Today, power grids are larger, more interconnected, and more complex than they were in 1989. Extra high voltage transformers, the backbone of long-distance transmission, are massive machines weighing hundreds of tons. They are custom-built, they are expensive, and they are not stocked in warehouses in large numbers. If multiple transformers were damaged across continents at the same time, replacement would not be measured in hours. It could take months, possibly longer. Electricity is not just about light. It powers water treatment plants and pumping stations. It runs fuel pipelines. It keeps data centers operational. It supports hospitals, air traffic control systems, and financial networks. Without power, communications falter. Cell towers fail once battery backups are exhausted. Internet infrastructure depends on continuous supply. Banking systems rely on servers that must stay online. Food distribution networks are tightly scheduled and electronically coordinated. Refrigeration, transportation logistics, payment systems all depend on electricity. When the grid goes down, modern life does not simply pause. It begins to unravel. In the first hours, people assume it is temporary. In the first day, concern grows. After several days, supply chains strain. Gas stations without power cannot pump fuel. Grocery stores cannot restock without functioning logistics networks. Urban populations, accustomed to constant availability, begin to feel pressure. Emergency services prioritize critical infrastructure. Governments activate contingency plans, but resilience varies by region. Some rural areas may adapt more easily than dense metropolitan centers. The question is not whether society would survive. It would. The deeper question is how quickly order could be maintained while complex systems reboot. Because a modern solar superstorm would not destroy civilization, but it would test it, and it would reveal just how dependent we have become on invisible currents flowing quietly through wires above our heads. To understand how far-reaching the impact could be, we have to look beyond cities and into the systems that quietly sustain daily life. Water is one of them. Most municipal water systems rely on electrically powered pumps to move millions of gallons through treatment plants and distribution networks. Gravity alone is not enough for modern urban populations. If power fails for an extended period, backup generators may keep facilities running. But fuel is finite. Resupply depends on transportation. Transportation depends on fuel pipelines, and pipelines depend on electricity. It is a chain. Hospitals are another pillar. Critical care units are designed with redundancy. Generators activate automatically, but even the most prepared medical centers rely on a steady supply of fuel, medication deliveries, sterile equipment, and digital records. A prolonged, widespread grid disruption would stretch those systems thin. Then there is the financial backbone. Electronic payments dominate modern economies. Card transactions, online banking, digital payroll systems all require functioning data centers and network infrastructure. Many have layered backups. Few are designed for weeks of continental-scale disruption. In the early days of a blackout, communities often respond with cooperation. History shows this repeatedly. Neighbors share resources. Local authorities coordinate assistance. But as days extend into weeks, strain accumulates. Urban density becomes a factor. High-rise buildings depend on elevators and pressurized water systems. Food storage in apartments is limited. Traffic control systems fail without power. Public transit systems stall, and information becomes scarce as communication networks falter. Contrast this with regions where lifestyles are less electrically intensive. Communities accustomed to intermittent power or localized self-sufficiency may adapt more fluidly. The impact would not be uniform. It would vary by geography, infrastructure age, grid design, and preparedness. Power grids are interconnected for efficiency. Interconnection allows energy to flow across states and borders, but it also allows disturbances to propagate. A severe geomagnetic storm induces currents in long transmission lines, especially those oriented east-west at high latitudes. Some transformers are more vulnerable than others. Engineering improvements have been made since 1989. Monitoring systems now track solar activity more closely. Operators can take protective measures if warnings arrive in time. Load can be reduced. Equipment can be temporarily isolated. But warning windows are not always long. Coronal mass ejections travel at variable speeds. Some reach Earth in days. The most extreme events can arrive faster. The Carrington Event of 1859 remains the benchmark. Telegraph operators reported sparks leaping from equipment. Auroras were visible near the equator. If a storm of similar magnitude struck today, the consequences would be measured not in damaged telegraph lines, but in disrupted power grids and satellite networks. Satellites themselves are vulnerable. Navigation systems depend on them. Timing signals used by financial networks depend on them. Communication relays depend on them. Modern civilization is layered: grid, satellite, fiber, pipeline, each resting on the assumption of continuous power. The question becomes not simply whether a storm could occur. It has. The question becomes whether resilience has kept pace with dependence, and that answer is still evolving. Resilience is not a single switch that can be flipped. It is a spectrum. Some utilities have invested heavily in hardening transformers, installing surge protection, and developing rapid replacement strategies. Others operate aging infrastructure that was never designed with solar superstorms in mind. Large high-voltage transformers are not simple components. They are massive, custom-built machines that can weigh hundreds of tons. Manufacturing them can take months. Transporting them requires specialized logistics. If multiple units across a continent were damaged simultaneously, replacement would not be immediate. Governments have conducted exercises modeling extended grid failure. Scenarios often examine cascading effects, how loss of electricity influences water treatment, healthcare, fuel distribution, and communication. These exercises do not predict collapse. They identify pressure points. Rural cooperatives may face different challenges than dense metropolitan utilities. Some regions can isolate portions of their grid. Others are deeply interconnected. Interconnection spreads load efficiently in normal times. During disturbance, it can spread instability. Solar activity follows cycles. Roughly every 11 years, the sun reaches a maximum of increased flare and sunspot frequency. But extreme events do not strictly obey averages. They are rare. They are unpredictable in exact magnitude. Space weather forecasting has improved significantly. Observatories monitor the sun continuously. Satellites positioned between Earth and the sun provide early data on incoming charged particles. This offers operators precious minutes to implement protective measures. Minutes matter. Protective shutdowns, however, carry trade-offs. Shutting down sections of the grid preemptively can prevent damage. It can also create immediate disruption. Decisions must balance risk against continuity. Beyond infrastructure, there is the human dimension. In a prolonged blackout, routine habits are disrupted. Supply chains that operate on tight scheduling begin to strain. Grocery inventories are typically calibrated for rapid turnover, not long-term storage. Fuel stations rely on electric pumps. Without backup generation, they cannot dispense fuel. Urban residents may feel impact more quickly due to density, but rural regions may face longer restoration times due to distance and resource allocation. Communication shapes perception. If cellular networks degrade, misinformation can spread through rumor rather than digital channels. Trust in institutions becomes critical. History shows that communities with strong local networks, volunteer organizations, neighborhood groups, mutual aid structures, adapt more effectively. Preparedness is not solely technological, it is cultural. It involves planning, education, and realistic assessment of vulnerability. A geomagnetic superstorm would not erase knowledge. It would test coordination. It would test redundancy. It would test how well complex systems were designed to withstand rare but plausible extremes. The probability in any given year may be low, but over decades, low-probability events become statistical realities. The modern era has not yet faced a Carrington-scale storm. That absence does not guarantee immunity. It simply means the question remains open. And in the space between solar physics and urban life lies a delicate balance, one that depends on foresight as much as engineering. If the lights went out across multiple regions at once, the first hours would feel surreal, not catastrophic, not cinematic, just quiet. Elevators would stop between floors, traffic signals would blink and then go dark. Office buildings would empty as emergency lighting activated and then slowly faded. Airports would ground departures until backup systems stabilized. Hospitals would transition to generators, a routine they practice for, but those generators depend on fuel deliveries that assume functioning logistics. Most people would expect the outage to be temporary. We are conditioned by storms, by downed lines, by local disruptions that resolve within hours. The first day would pass with cautious optimism. By the second day, patterns would shift. Mobile networks would begin to thin as battery backups deplete. ATMs would not function. Credit systems would stall. Digital payments, which now represent the majority of transactions, would become inaccessible. Fuel distribution would slow without powered pumps and coordinated routing systems. Water systems, too, rely on electrically powered treatment and pressure management. In some regions, gravity-fed systems would continue briefly. In others, boil advisories would follow once backup power cycles ended. Refrigeration would fail in homes and small businesses. Supply chains calibrated for efficiency rather than redundancy would strain under uncertainty. By day 3, the psychological shift would become more visible. Without reliable information, speculation fills space. Communities with strong local ties would begin organizing resource sharing. Others might experience tension born from ambiguity rather than malice. Law enforcement and emergency services would prioritize critical infrastructure. They, too, would operate under constrained communication. In highly urbanized environments, density amplifies both cooperation and stress. In rural areas, distance complicates response times. Neither setting is immune. Both present different challenges. Weeks into a sustained outage, if damage proved extensive, the defining variable would be restoration capacity. If grid components were intact and only temporarily tripped offline, recovery could proceed in stages. If physical damage to high-voltage transformers were widespread, replacement would require manufacturing timelines measured in months. During that interval, rationing of power might become necessary. Rolling blackouts could stabilize partial restoration. Industries dependent on continuous electricity, data centers, manufacturing plants, cold storage, would need contingency protocols. Global markets, tightly synchronized by digital infrastructure, would feel secondary effects. Satellites exposed to elevated radiation could experience anomalies, affecting navigation and timing systems. Even subtle timing disruptions can ripple through financial and communication networks. Yet history also shows that societies adapt under constraint. Improvised solutions emerge. Analog tools reappear. Local production gains renewed importance. Resilience is not an abstract ideal. It is the accumulation of small preparations at household, municipal, and national levels. Backup generators are one layer. Transformer hardening is another. Stockpiling critical components reduces replacement lag. Clear public communication reduces panic. Solar superstorms are not speculative fiction. They are astrophysical events with measurable precedent. Whether the next extreme event arrives in years or decades, the underlying question remains practical rather than dramatic. How interdependent have our systems become? And how intentionally have we prepared for the rare moment when that interdependence is tested? The answer will not be revealed in headlines. It will be revealed in how quickly normalcy returns and how well communities sustain themselves while it does. When we imagine large-scale disruption, we often picture dramatic collapse. But history suggests something more complex. In 1859, when telegraph systems failed, society did not end. It adapted. In 1989, a geomagnetic storm collapsed portions of the Quebec power grid. Power was restored within hours for most customers. In 2003, a cascading blackout left over 50 million people in the northeastern United States and parts of Canada without electricity. Within days, service returned. Each event exposed vulnerabilities. Each event also revealed capacity. The modern electrical grid is not a single switch. It is a network of networks. Regional operators, interconnections, redundancies, safeguards designed specifically to prevent cascading failure. Since earlier storms, monitoring of solar activity has improved. Space weather forecasting now provides advanced warning windows measured in hours to days. Grid operators can reduce load, temporarily disconnect vulnerable components, and isolate segments to limit damage. Satellites can be placed into protective modes. Aircraft can adjust routes away from polar radiation exposure. These mitigations do not eliminate risk, but they demonstrate that awareness changes outcomes. The deeper question is not whether a solar superstorm could occur. It can. The question is how civilization balances efficiency with resilience. Over the past century, we have optimized for speed, cost, and connectivity. Those choices have delivered extraordinary prosperity. They have also tightened the coupling between systems. Power supports communication. Communication supports logistics. Logistics supports food, fuel, medicine. Interdependence amplifies productivity and exposure. Yet resilience does not require retreating from modern life. It requires intentional layering, hardened infrastructure, distributed generation, localized backups. Informed citizens who understand that temporary disruption does not equal permanent collapse. The sky has burned before. Auroras have reached tropical latitudes. Magnetic storms have surged through metal wires. The planet endured. Civilization endured. and each generation gained a clearer understanding of the forces that surround it. If another great solar storm arrives, it will not test whether humanity survives. It will test how well we planned, how well institutions coordinate, how calmly communities respond, and how quickly systems designed with foresight can absorb the shock. In the end, the real story is not catastrophe, it is preparation. Because the sun will continue to flare. The Earth's magnetic field will continue to shift and shield, and modern civilization, aware of both its power and its fragility, will decide, long before the next storm arrives, what kind of resilience it intends to build.